In a variety of quantum condensed matter materials, the low-energy magnetic and electronic degrees of freedom can conspire to stabilize long-period modulated structures. Examples include vortex lattices in type II superconductors, as well as spirals and skyrmions in novel magnets. These modulated structures have length scales that extend far beyond the atomic unit cell and into the mesoscale regime that extends over tens of nanometers and longer, and which is naturally addressed using the small-angle neutron scattering technique.
We routinely perform diffraction studies of such structures using the small-angle neutron scattering instrument SANS-1. We use the instrument as a long-wavelength neutron diffractometer in a transmission geometry, where we detect the diffracted beam using a two-dimensional multi-detector placed behind the sample. Since scattering angles are just a few degrees, the use of the 2D detector allows an efficient survey of the diffracted beam, and it is often possible to measure multiple diffraction peaks simultaneously in just a single measurement.
The majority of quantum matter studies that we perform here at SANS-1 make use of high-field cryomagnets with variable temperature inserts, since this apparatus provides an in-situ control of the key low-energy degrees of freedom that underlie the stability of the mesoscale order. Here we have a 6.8 Tesla horizontal magnetic field installed onto a bespoke sample table at the beamline. And we have installed a single crystal sample of a skyrmion lattice hosting material into the sample chamber so that inside the magnet it is positioned at the height of the neutron beam. The sample is now under magnetic field and temperature conditions which are sufficient to stabilize a skyrmion lattice texture inside our sample. And now, with the instrument configured correctly and the magnetic field applied along the neutron beam, we are ready to perform the diffraction measurements. And here we see live on the detector the characteristic six-fold symmetric diffraction pattern due to a skyrmion lattice spin texture inside the sample and with a characteristic length scale of order 100 nanometers. It is also easy to study this spin texture as we vary the magnetic field and temperature. A great advantage of using SANS with cryomagnets are the ease and speed at which one can change the measurement geometry. Motorized stages provide in-situ rotation of the entire cryomagnet, allowing the study of other orders propagating in the sample along different directions. Now we are rotating the cryomagnet 90 degrees so that the magnetic field and sample are aligned perpendicular to the neutron beam. When we perform the diffraction measurement in this geometry, we see that the SANS diffraction pattern is dominated by two diffraction peaks. This is due to a spiral type of magnetic order that propagates along the field direction and which could not be observed in the first geometry. This ability to rotate the magnet between geometries provides the opportunity to study multiple modulating structures inside a single sample in a single experiment. For further flexibility, a motorized stage on top of the cryomagnet provides in-situ rotation of the sample inside the magnet, and thus independent from the direction of the magnetic field. At SANS-1, the diffraction measurements outlined here can be performed using horizontal field cryomagnets that provide fields up to 11 Tesla, or vertical field cryomagnets that give fields up to 10 Tesla, and using bespoke inserts, temperatures down to 50 millikelvin, or even above 500 Kelvin. A clear advantage of using SANS with cryomagnets are that the technique provides an efficient way to survey the collective and simultaneous response of multiple propagating orders in a single sample in a single experiment. In magnetism, the technique is generally fast and it provides an efficient overview of the mesoscale order phase diagram. This can be crucial for identifying novel phases which require deeper interrogation through wide-angle neutron diffraction or low-energy neutron spectroscopy.